For Lab 5, using Newton's second law, I predicted the total distance traveled in the motion of the volleyball with a constant force of friction acting on it and used my data to determine the kinetic coefficient of friction of the carpet. I found that by observing the volleyball's initial velocity, I was able to accurately predict the total distance the volleyball would travel before coming to a rest with constant force acting in the direction opposite to the ball's motion. By assuming that we can neglect air resistance and the carpet's frictional force is the only force attributing to the net force acting on the ball, by using Newton's second law, I also found that we could determine the carpet's kinetic coefficient of friction in relation to the volleyball. In my specific experiment conducted in my residence hall lounge, I found that the kinetic coefficient of friction between the carpet and the volleyball was equal to 0.0138. Now, these are some of the physics principles I use in my calculations and observations. The net force acting on a system is the sum of all forces acting in both the x and y components of the system. The object's velocity is equal to the change in distance over the change in time. I use this to calculate the ball's initial velocity. An object at rest has a velocity equal to 0 meters per second. Calculating the change in velocity from our initial to 0 over a period of time, I can calculate the net force acting on the object by using Newton's second law. Since the system is not moving in the y direction, we know that F net y is equal to 0, meaning the normal force has to be equal to the gravitational force acting on the system. That leaves F net equal to F net x. With the calculated normal force, we can also determine the coefficient of friction. I used the diameter of the volleyball to calibrate my video. I set the origin of my coordinate system at the center of the ball. That way, I could more accurately track the data as the ball moved in the x direction. I included the ball's mass in my code here. Then, in order to avoid the initial acceleration of the ball after applying the force of my hand, I started to track my tracker data once the ball was already in motion. I used the ball's initial position to initialize the ball's position in my computational model. Using the first data points of the ball's change in position over the first frame of time, I found my initial velocity and inputted that data into my computational model as well. Having the initial velocity and assuming the frictional force of the carpet is the only force acting on the ball, I calculated what the net force acting on the ball would be and inserted that into my code as well. The computational model. The VPython code updates the velocity and position of the ball after every small time interval delta t for the same length of time the ball traveled on the carpet floor. I pulled the exported CSV file that contained the computational model and compared it with the data I tracked on Tracker. Although the computational model shown in blue follows a smoother path than the experimental model, we can see here that they both follow a similar and close path of motion. At about 3.7 seconds, both show a stop in the increase of the object's position in the x direction. The variation in the two models is most likely due to an inaccurate tracking of the ball's center of mass on Tracker. Also, although I was indoors and assumed we could neglect air resistance, there may have been a small amount acting on the ball as well. Lastly, because the carpet is not completely a flat surface, the initial overestimate in the ball's position could be due to a non-constant force acting on the ball as well. What if? If the ball were hit with a greater initial force, the initial velocity of the ball would increase, causing an increase in the system's overall change in velocity as well. However, this increase in the system's change in velocity will also cause an increase in the length of time until the object comes to rest. Therefore, the initial force applied to the ball does not affect the magnitude or the direction of the frictional force acting on the ball while it is in motion. And we could still repeat this experiment to calculate the coefficient of friction of the carpet regardless of what our initial force applied is. In conclusion, my lab demonstrates how we could predict the frictional force acting on a ball by analyzing its change in velocity during the time it takes for the ball to come to rest. Both the computational and experimental model showed consistency in our predicted motion of the ball with constant frictional force acting on it. Using that information, I determined the kinetic coefficient of friction of a surface, here the carpet.